it actually helps us too. It will lead us into even better things, bigger and better things that'll help us out tremendously. That's what this integral test will allow us to do, among other things. Now, to use the integral test, you have to have there are some parameters here. For your series, a sub n, before you can use the integral test, the a sub n's have to be in a certain arrangement here to use the integral test. The a sub n terms are positive and decreasing. Positive and decreasing, because we have seen some negative or alternating stuff, alternating terms. Some sequences have negative terms. But to use the integral test, a sub n kind of has to be nice. They have to be decreasing. They have to be positive also, the a sub n. So it's limited in that regard. Okay? So here's the actual integral test. The series sum of your a sub n's is convergent if and only if the integral of f of x dx converges where for the f of x, we're saying the f of n is your nth term. Yeah, so this f of x is going to match your expression here for your terms of your sequence series. All right, so here's kind of restating this. This if and only if, it's pretty strong. Not only does it mean this converges if that, but it's vice versa. And there's also some other connotations here. If the sum, we're going, oh, I forgot one thing. It's 1 to infinity. It is an infinite improper integral we're talking about there. Here's how we'll use it, though. What we're saying, though, is this. If you have the integral 1 to infinity f of x dx, f of n equals a sub n, that converges, then so does the series. That's exactly what it says, okay? Series converges. But what you also might note is the other way, so to speak, is true too. What if I have the integral 1 to infinity f of x dx diverges? Because sometimes one thing tells us one thing and then the other may not be conclusive, but in this case it is. If one's divergent, the other is. If one converges, the other is. So, yeah, if it diverges, then so does the series, okay? Everybody okay with me on that? So what we're going to do is we're going to convert this, so to speak, to an integral. And then evaluate the integral. And if the integral is convergent, then so is the series. If it diverges, then so is the series. Okay? All right. Let's use the integral test to determine if the sum of the 1 over n squareds is convergent. Use the integral test to determine if the series 1 over n squared is convergent. Okay? So, what is the integral that I shall look at for this scenario? Well, I'm going to look at the integral of this. I'm going to change it over to x's. Look at the integral 1 to infinity of 1 over x squared dx. And that's not too terribly difficult of one, isn't it? That is just 1 to infinity x to the negative 2 dx, and that's just power rule, isn't it? Well, it is an improper, so we have to do our, remember what we do there? Limit, do the t limit thing. T goes to infinity. 1 over t, x to the minus 2. That's what we do here. And so, yeah, the integral part is just, it's not too bad. What would it be? Negative x to negative 1? 1 to t, so it's limit as t goes to infinity, negative t to the negative 1 minus negative 1 to the negative 1. Right? Which is t goes to infinity. I'm going to write that as negative 1 over t, and that's going to be plus 1. What do you got there? What's that limit? It's 1, isn't it? Yeah. T goes to infinity, so that goes to 0. That goes to 1. So that's a limit of 1. What does that tell me? Well, that's the integral of 1 over x squared. So what does that tell me about the series? Well, this is convergent integral. So the integral converges. So the series, the corresponding series does also. Okay? Is that okay? Now, here's kind of the graphical aspect to that. 1 over x squared, the integral, we're talking about the area under the curve. From 1 to infinity, so we're looking at this, right, where this x is, well, maybe not that tall. Maybe the expanded version of it. Let's do it that way. Here's 1, 2, 3. Okay, so we got 1, 1, 1/2, or 1/4 actually. Maybe it comes down a little bit lower. 1/4, that'd be 1/9. Yeah, okay. All right. So this corresponds to this area under the curve, right? Well, what you can do for this, to kind of put this alongside of it, think about the little rectangle there, and there, and there. What is this right here equivalent to? Isn't that, it's 1 times 1 squared. 1 over 1 squared. This is 1 times 1 over 2 squared, that box, or the rectangle. And then this would be 1 times 1 over 3 squared as far as area goes. Each one of these terms corresponds to the term of the series, right? Because the terms of this series would be 1 over 1 squared, 1. The second term would be 1 over 2 squared, 1/4. 1 over 3 squared. Well, doesn't that equivalently line up with those? I show you that because compare the sum the sum of those, the boxes, the rectangles, with the area under the curve. Isn't the area under the curve bigger? So if this is 1 under the curve, then isn't the rectangles less than that? So they have to converge also. That's kind of what we're saying. All right. But anyway, of note, yeah, this series here, right here converges. That's a new series for us that converges, I think. I don't think we've talked about that one yet. We're going to talk a lot more about it, though, here in just a second. Okay? All right. Here we go. If, let's use the integral test on this one. A lot like the other one, but it's 1 over the square root of n. Let's use the integral test on that. All right, so what integral are we looking at for this one? Well, it would be 1 to infinity over 1 over the square root of x dx, which is, using our t-limit definition, limit as t goes to infinity, 1 to t, that would be x to the negative a half. Well, let's see what happens there. What is the antiderivative of x to the negative a half? Well, that's the limit as t goes to infinity. Add 1, so it will be x to the 1 half, so it will be 2x to the 1 half from 1 to t. Believe that? All right, so that's the limit as t goes to infinity of 2t to the 1 half minus 2 times 1 to the 1 half. So that's the limit as t goes to infinity of 2 square root of t, basically, minus 2. What you got there? What's happened to that limit? T is going to infinity. So what's the limit? What happens to that term? That goes to infinity. Of course, that goes to 2. Infinity minus 2. It's infinity, isn't it? Yeah, minus 2 is pretty insignificant and considered to infinity. All right. So, what does that tell you about the series? Well, the integral diverges. So does then the series. So making that one little change, instead of n squared, I've got the square root of n, but it makes a whole big difference because that series diverges. Okay, now the way you can look at that one, graphically speaking, why that works is make our rectangles a little differently. 1 over the square root of x, it looks, well, it'll be 1 over 1, 1 over square root of 2, at 2, and then 1 over square root of 3. Looks a lot like 1 over the other, but slight difference there. But how we can get this action, instead of making the rectangles that are smaller, couldn't I say, like, this is the first term? Not exactly like I'd want it, but wouldn't that be the first term? First term? Okay. Then this is the second term because it's the area, right? And this is the third term. Well, if I do it that way, how do the rectangles compare to the area there under the curve? Isn't the area of the rectangles bigger than the area under the curve? So, if the area under the curve diverges, wouldn't the area of the rectangles diverge also? That's kind of the idea behind the integral test. You can make your rectangles go this way or this way, whether you want it to converge or diverge. But compared to the area, yeah, this area is going to be greater than that. And that's infinity, so that's also divergent. You see? With me? Okay. All right, so that's how the integral test works. So let's do a couple of those, and then we'll make some more points about those two that we just did. All right, so Let's use the integral test on this one. We can do other things besides just those basic ones. Let's use the integral test for it. 2 over n plus 1. Use the integral test there. It 2 will work. What do we got? Integral 2 over x plus 1, 1 to infinity. Yeah, dx. How are we going to do that one? Well, t limit, so it'd be limit, t goes to infinity, 1 to t. How are we going to do that integral? Well, use your same basics on those. Any thoughts? It's U-substitution. U equals x plus 1, du equals dx. That works out well, so that's limit t goes to infinity. It's 2 over u du, isn't it? What is that? Antiderivative. Integral. It's ln, yeah, it's ln. Nothing else, this is just good. And we're talking positive, so we can just use u. U is x plus 1. And we're going from 1 to t. All right, so plug that in. You got limit t goes to infinity, 2 t ln of t plus 1 minus 2 ln of 2. Well, I'm seeing this as a lot like that other one, isn't it? What does happen as t goes to infinity? What happens to infinity plus 1? What happens to the ln? Ln of infinity? Still infinity, isn't it? Because the ln graph keeps rising. So ln of infinity is still infinity. Okay, so that's infinity minus a number. It's infinity, isn't it? The integral diverges. So what happens to the series? Series diverges. So it's a useful little tool on some of these. Yeah, let me mention this one other one. One other one that might be handy to know. And then we'll get to our really good stuff. All right, series 1 over n squared plus 1. Integral test on it. All right, so we're looking at the integral 1 to infinity 1 over x squared plus 1 dx. Well, that's the limit. T goes to infinity of 1 over x squared plus 1 to t dx. That's actually a nice one. Antiderivative. What's the antiderivative of 1 over x squared plus 1? Remember? Tan inverse. Just to remind you there. All right, so this is tan inverse of x from 1 to t. So it'd be tan inverse of t minus tan inverse of 1. Well, easy one first. What's the tan inverse of 1? What angle gives you tangent of 1? You thinking pi over 4? Pi over 4, okay. So it's minus pi over 4. That's just a number. So we have the tan inverse of t minus pi over 4. Is that also infinity? No, it isn't. As t goes to infinity, think about the graph of y equals tan inverse of t. Remember, tangent has these vertical asymptotes, like that. Tan inverse flips that around, where we have horizontal asymptotes. And if we go this way, this is pi over 2, and if we go this way, it's minus pi over 2. But a pertinent note here is this side, right? As t goes to infinity, the tan inverse goes to what number? Pi over 2. Yeah, the limit as t goes to infinity, that's pi over 2.